Please welcome Rana Gujral, CEO of Behavioral Signals, who will take us beyond deep learning and to the cognitive AI frontier. In this talk, Rana will delve into a fascinating world of cognitive AI, shedding light on how this technology is pushing the boundaries of traditional AI models. Let us discover how cognitive AI is revolutionizing industries, enhancing problem-solving capabilities, and offering a glimpse into the future of intelligent systems. Be ready to embark on a journey beyond deep learning and into the uncharted territory of AI's transformative potential. Rana, please welcome to the stage and to DSC.
Thank you. All right, good afternoon, everyone. You gotta bear with me. I'm trying to shake off this cough for the last 10 days, but it doesn't go away. So if I started coughing in the middle, you know what's happening. We'll talk about cognitive AI. It's a field that I've been involved in for quite some time. I had a prior implementation of AI or deep learning with my previous company, Ties, which was acquired by Alchemy. And at that point, we were thinking about, okay, let's solve a bigger problem. And the problem that we focused on was essentially understanding human consciousness and various aspects of cognition in general, and building these cognitive AI models, which in many ways are building blocks of AGI, which is certainly a work in progress. So at the moment, we largely rely on AI for automation, but we are slowly and more so depending on it to augment human decision-making. But the human decision-making is very complex. I mean, if you just take a single decision and you look at the amount of data that a human brain processes, it's in terabytes. And so it's not really necessarily very easy to replicate the human decision-making process in an AI model. But once we get there, we potentially have this situation where we could not just have AI help augment decision-making, but in fact, it could just make the decision for us, which would be very interesting, and some use cases very relevant as well. So if you're thinking about the human decision-making process, I mean, it's, as I said, relatively complicated process. And also, the important thing to understand is that human decision-making ability is not necessarily logic-driven. Logic is definitely relevant, it's important, but it's not the only thing. The human brain takes in a lot of other data points, such as various aspects of emotions and behaviors and other mental cues from various modalities. You know, it could be from spoken word, tone of voice, body language. All of those goes into a human brain's decision-making process. And so the question then is like, well, okay, so that's how a human brain does it. How do we build algorithms that essentially allow us to make decisions in a manner that's similar to a human brain? So just, looking back, the last 10 years have been fairly amazing for artificial intelligence. It started off as sort of as a casual and a general exploration of what are the capabilities of deep learning and where do we apply deep learning. And from that, it has become a very robust and a thriving field with many applications, right? So you see implementations of recommendation engines in our online shopping platform, to object detection in a self-driving car, but also more recently, various generative AI implementations are producing very fluent and coherent text, which are fairly exciting and has a multitude of use cases. But with all its progress, deep learning has a lot of limitations. I mean, primarily, three things come to mind. This is not an exhaustive list, but in my opinion, these are some of the big ones. I mean, first, various deep learning models, they struggled with understanding context and nuance, specifically in natural language processing, which is obviously a hard problem to solve, but also without solving that, the deep learning and its progression is very limited. And then there's this question of bias. the models are as good as the data it feeds on and it sort of ingests. And if the data is biased, the accuracy of those models will be limited. And we see this in many early facial recognition models where the accuracy were limited because of the biases in the data sets. And then there is this big problem of transparency and essentially the aspect of black box AI. It's very hard sometimes to understand how AI is arriving at this decision. Some of these deep learning models are very, very complex. Even if you take a look at a simple model that is really built to determine who should get the loan or not, and you try to understand how that model has made that decision for either a loan grant or a rejection, it's not very clear. I mean, it's not clear how it arrived at that decision. So in many ways, it's a black box. And in many ways, if it's a black box, then it will be limited in terms of how it progresses or how you can help it progress further up. So when you're thinking about enhancing decision-making with AI, which is the goal, you have to first take a pause and think about how a human brain makes a decision. So the human decision-making process includes two systems of thinking. And this is the work that was done by Daniel Kahneman, which is really revolutionary, where he sort of measured various aspects of systems 1 and systems 2 thinking. So systems 1 is essentially the logical, the intuitive, the effortless part of the brain. It just makes decision, just out of nowhere. I mean, it's gut feel, it's intuitive. The systems 2 is more logical, it's pronounced, it's laborious, it's effortful. And that's where sort of, you're doing computations, etc. And if you look at all of the human decisions that we make on a day-to-day basis, 95% of the decisions we make are systems 1 thinking based. And only 5% of the decisions that we make are systems 2 thinking based. So that's typically how the human brain's running all day. But AI, or the implementations of the AI, or at least up till now, have largely been systems 2 based models. And so this is where you're sort of focusing on computations, processing large amounts of data sets, and that's not necessarily going to allow it to progress to a point where it can actually mimic a human brain. But what we're seeing now is a progression towards systems 2 level thinking, and using more and more, systems 1 level thinking, and using models that are sort of more intuitive and more, necessarily not based on computation and logic, but are based on more sort of like, unconsciousness, associativeness, and automatic pilot mode. And it's based on a lot of unstructured data. So what is cognitive AI? Right? So cognitive AI is an implementation or a model that tries to simulate the human thought process. And it leverages various capabilities such as data mining and pattern recognition, and also very definitely natural language processing to really mimic a human brain. And it's very different from traditional AI, right? So traditional AI is largely dependent on predefined algorithms and rules, and it largely tries to stick to those predefined algorithms and rules. And cognitive AI model is more adaptive, it's self-learning. And in that, you have the ability for these models to understand, reason, and learn from lots of unstructured data. And so these models can really make very complex decisions in a changing environment, which is very similar to how a human brain actually works. And so with implementations of cognitive AI, there's definitely now a shift towards a more intuitive, human-like AI, and going beyond just simple data processing, but necessarily focusing on understanding context, making judgments, and then also learning from experiences, very much like a human cognition functions. So the science behind cognitive AI is relatively complex, but at the end of the day, it's really using the tools that we already have. I mean, so such as machine learning, Machine learning allows AI to learn from experience very similar to a human brain does. I mean, you're going to have a hypothesis, you're going to shoot for a certain outcome based on certain data sets, and you're going to go see if your outcome or your determination of that outcome was on the right path or the wrong path, and if it's the right path, you double down on the weight factors. On the wrong path, you reject and you redefine those attributes. Similar to how a human brain sort of works in trial and error, that's how machine learning works. Very dependent on machine learning, also very dependent on natural language processing. And understanding language is a huge part of intelligence and building intelligent AI. And it's a huge building block for the cognitive AI models. The next big one is pattern recognition, and a human brain's expert in pattern recognition. It can look at various different things, aspects that it has never seen, and connect the dots and make determinations based on sort of what it's seeing now and what it's trying to achieve. And cognitive AI focuses a lot on building models that are focused on pattern recognition. But the last one on this list is probably the most relevant and the most complex and the big prize, which is emotional intelligence. This is sort of aspect of sentiment analysis, which has existed in some capacity for the last many years, but I'd say the granularity or the resolution of that has been fairly lacking, and also it has focused on some very obvious modalities such as facial expression, but also the spoken word, and spoken word's been very limited, so we'll get into some of the newer capabilities and techniques that go into it. But all of these put together are really essentially the building blocks of cognitive AI. So when we're talking about building cognitive AI, there's an aspect of emotions. A big question obviously comes up is, should machines have emotions? And interestingly, this question was actually posed to one of the founding fathers of AI, Marvin Minsky, and he had a very interesting response. He said, the question is not whether intelligent machines should have emotions, but the question is, can the machines even be considered intelligent without emotions? And that's really profound, because it is true, having emotional intelligence or having emotions or ability to understand emotions is a big part of being considered intelligent. And so if you're going to build intelligent entities, certainly if you get to a point of AGI, understanding emotions is very, very key. So then how do you actually do that anyways? How do you measure emotions? And certainly it's not as, say, concrete as other usual physiological functions such as, say, blood pressure or temperature. It's not really specific. But even though it's not, I'm fairly certain when someone's angry at me, even though they may be saying otherwise, right? It's very, very obvious. And so the human brain has this incredible ability to measure various nuances from different modalities, whether it's a spoken word, body language, tone of voice, and piece it together, which gives the brain a very accurate sense of how the other person that they're interacting with is feeling, what is their state of mind, how they're relating with the conversation that's progressing. And we can teach machines that. I mean, emotions and behaviors are essential, a part of our decision-making process, and we can also make it part of the machine's decision-making process. At the very high level, I mean, first you have to do two things. I mean, you have to first quantify and measure emotions, and second, then you have to be able to extract these emotions somehow, and that's a combination of using some sort of signal processing, BSP to be exact, but also then building complex deep neural networks that can extract these signals from various modalities, whichever modality is relevant. It could be the spoken word, facial expressions, tone of voice, etc. You can use these capabilities and generative AI to replicate essential brain functions. One of the things we've been focused on is the modality of the tone of voice, which is essentially not what you're saying, but how you're saying. So, really the intonations, prosody, pitch and tonal variance, everything outside of the spoken word. And that tells us a lot. So our engines, real time in a conversation, can extract signals that can roughly be put in 3 buckets. The first would be the bucket of emotions, like anger, happiness, sadness, etc. Then there is the bucket of behaviors. This is where you're looking at engagement, empathy, politeness, among other things. And then the third bucket is a collection of advanced mental states, such as, the experience, or measuring someone's experience with the other person when they're in a conversation with them, or their level of satisfaction. So think of this as a live NPS score. But also other things such as measuring stress, distress, duress, control. Control is really interesting. Control could be you're saying something, but maybe you're being forced to say it. Like, for example, there's a gun on your head, and so you can actually measure that, which is like what you just said, you didn't actually want to say it. And other aspects of intent modeling. So you're predicting intent to an action or intent to not do an action, and build very specific models that can predict what the person will do, relevant to the context of the conversation. All of these things can be done with various capabilities that actually exist today, and some of this is really our primary focus. You take these signals, you can do some really interesting things with it. So what we discovered is one of the things we could do is build what we call a conversational bioprint, or a behavioral profile, which uniquely represents a person's conversation style. And it's a combination of many different things, ranging from how fast you speak to various emotional, behavioral, aspects that you express in an engagement or in a conversation. And we learned that a conversational bioprint has three key attributes. The first is it's relatively and fairly comprehensive, and it uniquely identifies your persona in a conversation or an interaction with another human. And the second thing is that it is unique, which means your bioprint is one of a kind. And there are no two bioprints that are alike, very similar to a fingerprint. And the third is that it's either clashing with someone's bioprint or it's matching someone's bioprint. And this is something that you deal with every day in every conversation that you have. So there are conversations that you're having where your bioprints are matching, and you're having a natural, clicky, flowy conversation, irrespective of whatever you're talking about. And then there are conversations that are where your bioprints are clashing, and you want to get out of that discussion. I always like to give this example. If everybody in this room has been in one of the two situations. One is, let's say you're discussing something controversial, let's say politics, that's a favorite topic, right? With a friend or someone, and you're going at it, heated, and you're trying to change the person's mind. You can't. You walk out of it with, didn't change his or her mind, but, it was a good dialogue, it was a good conversation. And then the second situation is you just met somebody at an event like this or at a party, and you're having casual conversation, but in like 5 minutes, you're like, okay, somebody save me. Like, I just don't want to do this anymore. So there's just nothing you can do about it, right? And so, but once you have this information, now you have the ability to optimize certain experiences that could be relevant in a business setting, like, for example, call center, especially when you have a choice of who you're going to speak with. So if you call in, there's a person who answers who have been, uniquely picked for you and talks to you, and irrespective of their training or the ability to solve the problem that you have, you're going to have a great interaction and conversation, much better experience. So that's one of the capabilities that is now possible. And it has an oversized impact, right? So this is actually one of the implementations at a large public bank. This happened to be the largest bank in that EU country, name withheld for confidentiality. But they applied this technology in their call center that was dealing with loan restructuring applications. And in a very short period of time, in I think a matter of 4 months, we were able to measure this. They improved their loan restructuring percentages by 20%. So in actual numbers, if you think about this, it was $1.5 million per agent per year. And this particular bank had about, 300 odd agents, so it was like $400 or $500 million of net revenue generated by one simple technology that's just bringing the right people together. So now we're seeing sort of some of these implementations of generative AI that are massive game changers that were just simply not possible before. But emotive cognitive AI is not just useful in human-to-human interaction. It can significantly amplify human-to-machine interactions. So you could build virtual assistants that are emotionally and behaviorally cognizant, and it uses that information to interact with you to have a much better experience. So here's an example of an implementation. I hope the video plays. Let me click.
Published results on cancer causality perceptions yet?
I'm afraid not.
Ugh, shoot, what am I going to do now?
Maybe I can find results somewhere else. I will search further. Eureka! The International Human Genome Project has published some preliminary results on the number of study participants and their population diversity. Is that useful?
That is fantastic. Great find, Elsa. Can you upload? It would be great to add some numbers.
Already uploaded in your files.
So can you, Alexa, do that? No. But it would be really amazing when have that type of interaction with Alexa. And this has actually now been implemented, and it's definitely possible. But it's not just limited to virtual assistants. There's a lot of other machine interactions we're having, and not just the type of interactions that you're having with your car or your microwave, or you're interacting through voice, but these caregiver robots. So here's an implementation with Temi Robotics, and so this is a caregiver robot for folks who are living by themselves but need some sort of I'd say oversight and care, and it sort of shows the type of experience that you can build.
Good morning, John.
Morning.
John, it's time for your medication. Could you please retrieve your pills from the dispenser? John, please, take your pills.
You know what? Why don't you go somewhere else where you're needed, like maybe the kitchen?
Okay, I will go to the kitchen.
It's good. Bye.
There's a longer video that shows the full interaction. The robot actually comes back and decides that it's going to crack a joke to cheer this guy up, and eventually succeeds in having him take the medicine. And we actually filmed this in New York, in Manhattan, and we're looking for a subject. We found this guy I met, at an interaction. Is like, you're just the perfect grumpy guy. You need to be in this video. And he was just natural. And we were just worried that, the Temi Robotics, the machine itself, would actually, keep up with his emotional variance. But it was pretty good. So it's actually online. This video has some sort of a lag. I'm not sure, the lips are not synced, but the actual video plays really well. So that's human to human, human to machine, but cognitive AI is not necessarily just limited to call centers, or for that matter, various aspects of sort of robotics. It has some very interesting and powerful implementations in various use cases that are relevant to national security. And using cognitive AI, you could, model and track various behavioral states. When you can track behavioral states, you can also track variances from that behavioral states that give you essential cues, that allow you to make some determinations on the action that you're trying to predict. But you could also predict intent, which could come in very, very handy. language-independent surveillance, right? So all of these models, including the two models that you saw, one with the Lex implementation and Temi, there was a purely tone of voice AI. So it was, of course, like the emotion AI piece of it was not considering the spoken word, which means that you could be speaking in any language. You could be, speaking in a language that has no data sets for training. Doesn't really matter. It's just focused on intonations, and it's getting all of that data from that, and that's why the tone of voice is very, very powerful. And so with that, you can do language-independent surveillance, which is a nice, cool thing for the government. Deepfake voice detection, that's a huge problem. It significantly helps on detecting sort of various aspects of natural versus synthetic voice, understanding or assessing, threat from voice, and various aspects of Polygraph Plus, where you're trying to gauge someone's reliability or trustworthiness in various forms. And so a lot of these implementations are possible using cognitive AI. I want to show you this, this audio. So it's essentially what you're going to see is like there are 5 audio clips from 5 different movie scenes. They're in 5 different languages. And the reason I want to show you is to help you understand how powerful the tone of voice modality is. It's such a visceral modality that if you tap in, you oftentimes don't need anything else. You don't need the facial expressions. There's no video here. So you have no idea, what that scene is. Some of these languages may be completely, unrecognizable to you, and so you don't understand any spoken word. There's no closed captions. And so this is something you could do at your home too. I mean, you could pick an audio from a movie preferably, because there's something happening there, and see if you can figure out what's happening, right? And so in this case, obviously, there's the engine also analyzing it, but you'll see that even in the situation where you don't have the spoken word to rely on, you don't have the visuals, the facial expressions, any visual aspect at all, you're still very much able to follow on and understand what's happening. And it's really how we communicate with babies, how we communicate with our pets. Many people actually do believe that your pets understand everything that they're saying, the language. I mean, they don't, unfortunately. But they are able to function just okay, and at least convince you that they're understanding everything because of what they can decipher from your tone. And that's exactly how powerful that is. So let's play this.
Là, on croise la veuve du tambour de la fanfare. Elle porte la vareuse de son mari depuis qu'il est mort. Attention, hop! Tiens, l'enseigne de la boucherie Chevaline a perdu une oreille. Ce rire, c'est celui du mari de la...
後悔はしてない。俺の夢は叶わなかったけど。お前こんな風に死んじゃダメだ。うちに帰るんだろ。帰って一緒に走るんだろ。常識君。一緒に帰って一緒に走りたかったけど。Πες μου πως μετάνιωσες. Πως θα με παντρευτείς και το πετάω. Στέλλα, φύγε. Γιατί δεν φεύγεις! Γιατί! Θέλω το πελερίδα. Verga, agáchate. Tengo una pistola, cabrón. Cabrón, traigo una pistola, güey. Cargó la verga, cabrón. De una pinche.
Ladies and gentlemen, it's indescribable. I can hardly force myself to keep looking at it. It's so awful. The eyes are black and they gleam like a serpent. The mouth is kind of V-shaped with saliva dripping from its rimless lips that seem to quiver and pulsate. And the monster, or whatever it is, can hardly move. It seems weighed down by possibly gravity or something. The thing's...
Yeah, I think this is it. And so, again, as a reminder, only tone of voice base. I mean, the engine here does not have an ASR or a speech to text. It does not take the audio, convert that into the text, and then parse the text for meaning. It just purely sort of doing it from the tone itself. So, I mean, this is definitely where we're headed. I mean, cognitive AI is, the new frontier, and it is how we get to AGI. And we have a lot of these building blocks already. There's a few other missing pieces. I mean, it's also a very, very tough problem to solve. Certainly, there are aspects of human interactions and behavioral dynamic that are extremely complex, like sarcasm. But you're always sort of looking at the human ability and see if you can get close to the human ability. And when we first started to work on this, we were looking at sort of what's the benchmark. And this technology was in the research, at the SAIL labs, which is, jointly sort of partnered with USC and Stanford. And we were sort of at, the F-score of 0.5. Like this F-score is really a score between 0 and 1. And a human's brain's F-score, an average human's F-score is about 0.8. Which is like about roughly, if you think about it, I mean, it's a score which is a combination of precision and recall, so precision being accuracy and recall being false alerts. 80% of the time human brain is right, 20% of the time is wrong, but that's the best it can be. And some are better than others, but this is an average score. And so the models are at 0.5, and then we see a point of inflection, and it goes from 0.5 to 0.6, then it goes from 0.5 to 0.8 in 18 months. Currently we're at 0.92, which means the engines are performing better, not just equal, but way better than an average human. That's really powerful. But it's not a solved problem yet. It's really complex. Especially affect. Affect understanding is really challenging, which is affect is technical term for emotions. If you look at this picture and I poll everyone and say, tell me what do you think is happening out here, I bet I'll get a very diverse set of answers that range from everything. But when you see the full picture, that's when you see it. Like say, oh, okay. And so that's where the missing pieces are. But we are slowly sort of filling in the gaps and getting to that point. And this is it. Thank you, guys.
We have a nice time for questions. I would have a couple, but let's start with you guys. Here's the first one.
Hi, thank you. Thank you for the presentation. So I have several questions, but I'll go in the order of importance, so you can cut me off at any moment. There's a point in time when you mentioned that comparing people's bioprints, if that was the word, could kind of show you how compatible those people are or the likelihood of them having a good interaction. How is a good interaction defined in this particular case? And maybe another question is this bioprint a static vector for each person? Does it change over time? And also, how frequently is it expected to change? If you estimate it for a person, can you expect it to be the same tomorrow or for the rest of their lives or in the next couple of minutes?
Yeah, those are some really good questions. In fact, I think I've gotten a lot of questions. Those two are new ones, so I'm really happy that you asked those questions. So first off, I mean, in terms of sort of like, what comprises of that, I mean, again, the conversational dynamic, this is something that we just discovered, right? So there's not a lot of, I'd say, benchmarking in here. But what we've discovered is that, that there's a bioprint, and the bioprint currently sort of like, we're looking at about anywhere from 75 to 100 attributes. And the question is which attributes you put a higher weightage factor on, and that's determined by, and that sort of changes the flavor of the bioprint. That's determined by how you're going to use the bioprint. What's the actual purpose, right? Are you going to use it for dating? Are you going to use it for selling somebody something? Or are you going to use it to solve their problem and level of satisfaction? And so those are, again, unique models. I mean, and those models that focus on those different attributes. And we've sort of tested a few. I mean, the obvious ones. I mean, we've tested the one which is delivering the best customer experience. And then there's one that sort of builds sort of the sales sort of dynamic. And so you could fine-tune that, but what we've seen is like, when you extract all the data and you put it in that, it's like a vector file with all the sort of scores of all those sort of measures, you already have all the data. I mean, sort of reconfiguring it is instantaneous, right? So you could sort of like say, okay, so the bioprint, we were originally thinking of the bioprint as sort of how that performs in that interaction, but now we think of the bioprint as the whole, and we say, okay, well, which aspect of the bioprint you need to focus on for this interaction. So when the clients deploy the solution, they have a choice to pick the use case they want to optimize and say, I want to improve the satisfaction in my call center, and the matching algorithm essentially focuses on different dynamics of the bioprint and does that. It does evolve because it's really sort of linked to you physiologically, and so your bioprint today will potentially not be the same a few years from now as you evolve, but it's not evolving on a day-to-day basis. It's also not evolving based on how you're feeling at the moment. So for example, you could be calling in and you could be really angry and upset, but you're generally not an angry and upset person, and so the bioprint necessarily does take that into account. So it is sort of like more, who you are today. And then as you change, the bioprint changes.
Thank you. Thanks so much.
If I can follow on this just a little bit. If I was doing an interview with you, I would do research. And not only on what do you speak, but how do you speak. I mean, if this is going to be a video interview. So would your computer do a research on the people he is supposed to communicate with when we talk about creating this bioprint?
Yeah, so I mean, that actually is a very relevant sort of point of thought. Let's say, the goal of a bioprint is really to build good matches towards the purpose that you're trying to match people for. So in a call center, let's say you're trying to optimize your, either sales or customer experience, and you would see that there is a certain dynamic of your client base, and then there are certain profiles that are better matches for your client base. Now, there's no profile that's a good profile or a bad profile. Your profile is your profile.
But you're making profile after or during the conversation, are you?
Yeah, so,
there's no previous profile. You could know at the center who's going to call.
Yeah, so I mean, the profile is created in the first model of interaction.
Okay.
And it just takes about 1 minute interaction to create a profile. And so in a call center, you would have the first call be matched to a group of agents that are sort of in the neutral bucket. And then the second time will be a one-to-one match because you have the client's profile.
Okay. Here.
Yeah, thanks for the talk. Very interesting. So there was one statement that kind of surprised me a little bit, is that you said that this emotional intelligence doesn't change from language to language. You can generalize it, as you've shown in this example. So for me, I'm a person who's not living in the country which I grew up. So what I notice is that people not only speak differently, but also they sing differently, and it means different in that context, right? So as I'm sure, I agree there's a large intersection between different cultures, different languages, but I'm just wondering, what's the percentage of differences that some cultures have? So did you research this part of the field as well?
Yes, that's a great question. So, I mean, there are obviously tonal languages that generally just speak in high-pitched tones. Sometimes you feel like, people are fighting, but they're not fighting. They're just talking to each other. And then there are non-tonal languages that are more soft-spoken, right? So obviously, the tonal variance is quite drastic between different languages. Also varies by cultures and, different regions and et cetera. So the reason the engine doesn't care is because we have found that, so the simple answer here is when you're trying to measure a signal, let's just say it's anger or happiness, whatever. It's essentially you're looking to see, at what point, what is the point of inflection from a baseline where you're getting that signal. And certain points of inflection, represent that signal. So if you get where you're supposed to, you're expecting it to be anger, then it's anger. If it's at a different location, then it's happiness. And those points of inflection are identical across all languages, whether it's tonal, non-tonal, but the baseline changes. And so if you're working on a language set, which is tonal languages, it would be a different baseline, but the point of inflection from the baseline is relatively, so that the coding, the software behind the human brain is the same. There are some cultural variances that are making it specific. I mean, and it's another unique way that we're all the same. I mean, the inflections are the same. And so what we have to do is when you're working on a new data set, that is a new language, which we don't know or don't support, we have to recalibrate that baseline. And we could do it with like 5 to 10 hours of data. So we need about 5 to 10 hours of data, relevant data in that language set, and then run the recalibration process. It comes with a new baseline. And as long as the engine understands this is the language set and this is the baseline I need to use, it just works across the board. In fact, you could actually run it without baseline recalibration, and it's still relatively okay, but not top performing.
Thank you.
Yeah.
Can't see if there are any. Sorry, there is one hand raised there.
Who's got the mic? Okay.
So all the way there.
Thank you. Very interesting talk. So I come from the gaming industry, and one of the biggest problems we have in competitive gaming is the toxicity, basically, when people interact in their, very passionate play sessions and so on. Do you think maybe that this technology can be used to detect toxicity? It can definitely detect anger and stuff like that, so that maybe we can, influence the player in a certain way just to calm down a bit or whatever, ban them, I don't know. But toxicity can come in many forms. It can be irony, it can be, something smooth but still toxic and stuff like that. Do you think that maybe we can use something like this to try to resolve that problem?
Yeah, I mean, it definitely can be used, there's probably a dozen different companies focused on a dozen different specific vertical market use cases that can be built on technology like this. I mean, it could be a gaming experience, and augmenting a gaming experience could be on the healthcare side because it can measure vocal biomarkers, etc. So certainly, yes. I mean, we actually have an API that we allow others to use for non-commercial purposes, mostly for research. But if you're building something that you promise not to commercialize, we'll allow you to use those APIs as well. We do sort of do some select licensing on those commercialization, but that's very restricted in terms of sort of how we make that possible. But yes, there's definitely implementations. In fact, when you're one of the product implementations is like a real-time assist engine for a call center agent. So if a call center agent is speaking and having a conversation with a client, you don't need, by the way, you don't need the AI to help the call center agent, understand how the client is feeling, because the human brain is already doing that. So it understands whether the call center, the client is happy or sad or whatever. But the agent's not aware often of how they are reacting, whether they are angry or disengaged, or because they're zoned themselves out. I mean, this is the 100th call of the day. So the engine's focused on the agent and telling the agent to slow down, be more empathetic, you're sounding angry, similar type of experience. Yeah.
Okay, I think that will be about it. I just want to add one small question is about when you're doing these bioprofiles, do you need my consent if I'm the caller in order to make my bioprofile? I think that's quite an important legal issue.
Yeah. So, I mean, the regulation around cognitive AI doesn't exist because...
So that's the answer.
They're trying to, first of all, you have to understand something before you build a regulation around it, so it's just moving so fast. There is consent required for recording, and revealing that you're going to be using that recording to process or analyze, etc. So it's a typical consent that is required for, here's here's your call interaction, which will be recorded and used for quality assurance purposes, and that's typically what it is. The good thing with the bioprint is not PI data. Right, so for example, my bioprint obviously, is derived from me, but if you have my bioprint, you cannot identify me, right? So there's no personally identifiable information in the bioprint, so it's SOC 2 compliant, it's PI 2 compliant, I mean, it's GDPR ready. In fact, our implementations don't process the spoken word. There is no text to redact. There's no text that we create. I mean, we discard all the spoken word. It's purely the tone of voice AI engine, so you can't find someone's identity or reveal their privacy, from that data information. So it's incredibly private and secure. In fact, much better than previous implementations of speech-to-text models.
Thank you. Thank you. And may I present you
thank you.
with a certificate that you were a lecturer at DSC. Thank you, Rana.